So with that, I'm proud to turn it over to our special guests for today, Charina, Chou, and Dave Bacon of Google Quantum AI. Thank you for joining us.
Awesome. Thank you so much, Jay. Really happy to be here with you all. Dave and I are going to talk about Google Quantum AI, our progress and roadmap. And this session is really looking at, why build a quantum computer at all? Why is Google trying to do this? And how are we going to get there? What's the progress we've made so far? So with that first question, why build a quantum computer at all, right? And we certainly hear this often with increasing data centers and AI and all of these new classical computing tools. Do we really need a new type of computing? Are there questions that can't be solved by existing computing today? And the answer is yes. One way to look at why this is really useful can be summed up in this quote from Richard Feynman. Of course, a Nobel Prize winning physicist. He says this in a famous lecture from the 1980s: nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. Right. So what he's talking about here, look at all of these things around you in nature, right? Whether it's leaves, it's molecules, electrons, photons. At their heart, all of these things function quantum mechanically. And we can try using today's classical computing to simulate what's happening, to estimate, to make broad calculations. But at its heart, there are still many types of things we cannot understand, including exactly what molecules are doing at their fundamental level, how they are behaving in the excited state, how they're interacting with each other. If we could understand these things, we could really understand so much more about nature and really try to make a major dent in problems like battery development, pharmaceuticals, climate change, and others. So you can see here, right, the thesis at the top is quantum computers will be a powerful tool for computation. We talked about quantum simulation, literally this idea that was represented in the Richard Feynman quote, right? Like chemistry, like simulating what's happening at the physics level and what's happening in biological molecules. You can see that existing proofs demonstrate that there's expected to be an exponential speed up when performing some of these calculations on quantum computers relative to classical computers. That is when we've got, powerful enough quantum computers to run those calculations. There's other areas as well that are demonstrated to have speedups. For example, quantum machine learning. So that is learning from quantum data is expected to have an exponential speedup. Another way to think about this is that quantum computers will be able to learn from exponentially less data than classical computers when learning from quantum data. Factorization, of course, is an important topic, and one that through Peter Shor's algorithm published in the 1990s has also shown that quantum computers are expected to have a speed up for factorizing large numbers. And then there's a whole class of other types of problems like unstructured search, some types of optimization, and others where there's some speed up identified up through potentially exponential. And actually to date, over 60 algorithms have been identified that will demonstrate a quantum speed up once powerful enough quantum computers are here. And this is really what drives us, right? This is the mission of Google Quantum AI. Our mission is to build quantum computing for otherwise unsolvable problems. So how do we do that? You can see here on the screen the Google Quantum AI roadmap. So this is our roadmap to the type of computers that we think are going to be needed to solve the problems that we just talked about for the last few slides. So you can see here a set of 6 milestones labeled milestones 1, M1, all the way up through milestone 6, M6. And this is what we've labeled at milestone 6, an error-corrected quantum computer. So if you look at each of these milestones, there's a couple of things to notice. First, in the darker blue is the number of physical qubits. So you can see as we go from milestone 1 all the way through milestone 6, we're expecting to increase the number of physical qubits by about an order of magnitude. Now, it's important to note that the number of physical qubits, the quantity, is not the only thing that is listed here on the slide at each of these milestones. And, sometimes we'll hear comments like, oh, of course, it's all about scaling and getting to larger numbers of qubits. Of course, you are going to need more qubits to get to a better computation, but you're also going to need a higher quality of qubits. So you can see in the lighter blue, we've also listed a target logical error rate that we want to get to. That is the number of errors that we expect per computational step. So for example, at milestone 3, 10 to the minus 6 logical error rate, that is an expectation of targeting 1 error in every 1 million, 10 to the 6 computational steps. And this is really important for us to increase scale as well as quality to get to the kind of computer that we really think is needed. And a lot of the applications that we identified, we'll talk about what's possible at each of these milestones, but a lot of the applications we identified, true chemical, simulation, true understanding, quantum machine learning from quantum data, these kind of things are largely expected to be realized with a milestone 6 or better computer. And of course, you see the arrow continues to go to the right. So there's no reason why we or anybody in the field should stop at milestone 6. Just as with classical computing, we expect continued progress in the field. Now, where are we today? There's a star here, which notes we are here. So we demonstrated milestone 1 at Google in 2019. We demonstrated milestone 2 in 2023. You can see the devices, photos of the devices that we used to achieve those above the milestones. And Dave is going to talk through more detail of what those milestones entailed and the current progress that we've made. We're between milestones 2 and 3 and really trying to get there. And first, Dave will talk a bit about our approach, what quantum computing is, how it works, and then on the way to understanding the milestones.
Awesome. Great to be here to talk about this. So we're going to take a bit of a step back. So Karina sort of laid out the road path of where we're going. And I wanted to sort of get you some idea to sort of ground ourselves. And there's 2 ways to ground ourselves. One is sort of in the abstract, what is quantum computing, just so you really have a good picture in your head, both sort of like how should I think about it and how it's different. And then also, what is it physically? That's the second part. And these are very different things that we're doing every day in the quantum group. So the main thing about quantum computer that Karina said is quantum computers are different, right? This was the discovery in the 80s and 90s that quantum computers can solve problems faster than classical problems on certain problems. It doesn't give you a ubiquitous speed up everywhere, but there's classes of problems where quantum computers can give you speed up. So why is that? So I want to give you a picture that you can have in your head. You'll hear words, people will say superposition, entanglement, they'll use those words, but those words aren't that useful. I think what's more useful to have is sort of this picture of what's actually occurring in quantum computation. So to take a stab at that, we first start with like just a classical computing slide. So you have some bits in your computer. Here we have just 2 bits, which I guess is a quarter, right? 2 bits sitting there, and we can do some operation of those bits. They start in 0, 0. We can flip the second bit. We can flip the first bit, and then we can flip the second bit again, right? And what happens as a function of time, as we're flipping it, the bits change, right? And there's a path that system, that computer takes in, space in the data, and then the time. Okay, so that's fairly straightforward, right? Well, you may have heard quantum computers introduced. Quantum mechanics has probabilities in it. And so you might think, well, okay, what about if I allow myself some extra power in computing? What if I allow myself the ability to flip coins? And many of us know that probabilistic computing is often more powerful, or at least, can do things that it's very hard to get to work deterministically, as we call it. So you can imagine, what if I allow flipping of coins? That's probabilities. Maybe quantum mechanics gives us something there, but that's what we call probabilistic classical computing. So we could do something like, instead of flipping that first bit, we could say, 1/3 of the time, flip that bit, right? And so there's some probability that we now are in the 0, 0 state or the 0, 1 state. That's that first step there. Then we could do just something like, flip the first bit. That's a deterministic operation. And then we could do something probabilistic. So we can do these series of things where we're doing probabilities of different events. So if you do that, right, you have sort of this diagram. These are the possible states. At the end of this computation that I have here, you can be in the state 1, 0. That's this top line at the end here, or 1, 1. Okay. So then what you do is, like, you figure out, okay, what's the probability that I end up in 1, 0 at the end? And to do that, what you do is you just sum the different possible paths. So the computation is taking place in space and time, but we're having probabilities of these different paths occurring. So what you do is you multiply the probabilities along and you add them up together. So you get this number, and it turns out that it's 5/9 of the time you'll see 1, 0, and 4/9 of the time you'll get 1, 1. So you could run this repeatedly, and those are the probabilities you get. That's a probabilistic classical computer. So what quantum does, and this is not exactly correct, but is the right way to think about this, is you say, well, what if you could make a negative probability? Now, what does that mean? that's crazy, right? Like you're talking crazy talk. In fact, Feynman, who was mentioned by Craig at the beginning, has a very famous talk in which he talks about negative probabilities and tries to make sense of it. And that's sort of what that's the sort of best picture you should have in your mind for what quantum does. So let's say I added a -1 in here in this one possible path. Now that's like, this thing is transitioning from here to here, and instead of doing it with 100% probability, it does it with -100% probability, which doesn't really make sense. But you could try to put together a theory like that and say what happens. And now instead of doing this, adding these two separate paths, the black path and the red path, we would now have a minus sign in there because of that -1 in there. And what would happen is the probabilities would interfere with each other. They would destructively hit and make the probability smaller. Remember, previously it was 5/9, and now it's 3/9, 1/3. So what's happened is in space and time, this thing has exactly done this thing where it sort of decreased the probability, and that's what quantum computer does. Quantum computers, what happens is this evolution in space and time, these steps that you take, instead of taking a step with a certain probability, you take a step with a amplitude. And these amplitudes can be real numbers or pluses or minuses. They could also be complex numbers, which my son always insists are imaginary, which is a bad joke. But the important thing here is that you can make a complete honest version of quantum computing by just sort of making these things negative. Now, they're not exactly probabilities, they're called amplitudes. And then what happens is the computation progresses in space-time, and you can get these interference effects on the computational space. So the picture you should have in your head for quantum computing is really this picture. This is the picture instead of superposition or all this. It's that what's happening is the computation is occurring, and just like you have water waves, and when they hit each other, they can add or subtract. They kind of like interfere with each other or get bigger, right? This effect is occurring, but it's occurring on these amplitudes, which are essentially probabilities. When you square amplitudes, you get probabilities. So this means that you get these interference effects in space and time, and this is what quantum mechanics is. And in quantum computing, we're just building a computer that exploits that interference. That's how quantum computing works. So that's the abstract picture you should have in your head. What's the picture you should have in your head if you actually want to build one of the things? So on our team, we build superconducting qubits. There are a variety of different ways we can try to build quantum computers. Qubits are the basic zeros and ones of our system. This is a picture of two of our chips that were useful for Milestone 1 and Milestone 2. They're Sycamore chips. You can see a little bit of a thing in there. They're pretty big. I mean, you can see the dime. And what's going on here is we have superconducting circuits. So basically, we have little tiny, just normal circuits in there, with one exception. We have this thing called the Josephson junction, but they're really just little circuits, just like in sort of a normal computer. But they're superconducting, so they're cooled down to microkelvin. So they're cooled down to very, very cold temperatures. These are fabricated by us in one of the few superconducting quantum computer fabs in the world in Santa Barbara. And so we have the facilities to build these special chips, because they do have like this one special thing, this Josephson junction, and build these things from sort of ground up. We're really building, this is very much like building a classical computer from the ground up. And what we do is these things are packaged up. So there's a package here, and then there's a ton of wires. You can see one of our wiring stacks here. And this thing is the inside of what's called a dilution refrigerator. So this is the dilution refrigerator unpacked. We've taken off all the shells around it. And you see all the wires there. Those wires are all hooked up to this package. And inside that package, in the little middle part, is the actual chip. This is cooled down to 10 millikelvin. 10 millikelvin, the joke is always, it's colder than space, because in space you have the cosmic background radiation, which is like 3 Kelvin. So it's colder than space, but it's very, very cold, right? Just right above absolute zero. And what happens when you do that is you get superconducting circuits. So in superconducting circuits, what happens is the circuit is persistent. If you take a little loop and put a superconductor and put some current in it, it just lasts forever. And it exhibits a thing called macroscopic quantum computers. What that means is that actually behaves like a quantum system. We have this little Josephson junction. It makes it so that we can actually talk to that system and do computations on it. And what we do is we shoot signals down these wires into that chip to run a quantum computation. When we need to measure the system, we shoot signals in and watch for bounces back. But down at that lowest level, those superconducting circuits, those qubits, are doing this weird interference in space-time. Okay, so what have we done with the chip? So the first milestone they hit was what we call Milestone 1, which is our beyond classical benchmark. And in this experiment, what we were doing was in the early days, I've been in quantum computing for a long time. I was intern in 1996, one of the things that people started doing when Google first started their quantum effort was to try to start doing something with your quantum computer that was hard to simulate classically. So as Charina said, there's this idea that quantum systems, are out there and they're very hard to simulate on classical computers. And as they scale up, we don't have really good efficient ways to do that. And so the Milestone 1 benchmark is like, is there a problem you can do where if you throw your best classical HPC people at it, the best algorithms we have, this scaling blows up and it doesn't appear that we can simulate that quantum experiment. So this quantum experiment is called random circuit sampling. People say it's useless. I don't know what, it's a problem. You run a quantum circuit and you observe the outcome of it. And in this plot here, what we're doing is we're running this for longer and longer times. Our quantum computers, as was mentioned by Charina, are noisy. They don't do exactly what we want. And so the ability of us to run this gets worse and worse as we run it longer and longer in time. But when we ran this experiment, we were able to do a large enough quantum computation. So enough of that space-time volume, that big picture we had of space and time and what it's doing, enough of that was involved that when we ran our best classical algorithms at the time, it would take very, very long in order to simulate this. So at the time when we did this, we estimate, 100 years, 10,000 year timescales for Summit, the best supercomputer at the time, to do this. Now, we did that doing the best we could do. We got a red team that is very smart and tried to do this. But over the years, people have chipped away at that by building better and better classical algorithms or suggesting crazy things like our estimates didn't involve using all of Summit storage, but somebody suggests you use all of Summit storage. Turns out, I think the energy necessary to do that is like that of a nuclear powered power plant, so it's a lot of energy, so we didn't consider that realistic, but everybody has their own version of realistic. But over the years, it's sort of the classical people have improved. Our chips have also improved a little bit. So we recently ran it. This red is sort of like what this last generation chip could produce. And for the first time, this is an experiment where you're doing something that just classically we don't think you're able to keep up, right? And it doesn't solve an interesting problem or a practical problem yet, but it's exciting that we can do something that you throw the best, these smart geniuses who can do these classical simulations at it, and they're struggling to do it. The Milestone 2 is the next step that we did. As Charina said, that there's this problem that quantum computers are noisy. We can't control these. So we're shooting these signals in, and we're getting bounces off, and the quantum circuits are doing mostly what they're supposed to do. But they don't do exactly what we want them to do. They also are coupled to their environment. We try to isolate them. You saw that picture. There's the picture at the beginning. They're all in this giant dilution fridge. We're trying to isolate them. They don't want to talk to. We don't want them to talk to anybody except the control signals we're sending in. In Milestone 2, what we did is we showed for the first time that you could get error correction to work. So what is error correction? Error correction is the idea of taking a bunch of noisy quantum bits and distilling out one good quantum or multiple good quantum bits out of it. So you might take, say, 50 physical qubits, they'll call them, so real circuits, so 50 loops down at the bottom level, and then you pull out of that one good qubit, and you do this dance called quantum error correction. So it's a specific algorithm you run on the quantum computer, and you run this and try to preserve the quantum information. Prior to Milestone 2, everybody who tried to do this experiment, the qubits were not good enough, and instead of becoming an error correcting experiment, it was actually an error worsening experiment. If you take more qubits, everything would always get worse. And the idea of error correction, which was a pretty amazing discovery, was that if you encode the information and do this dance, you have low enough error rates, you could actually get it to work. So Milestone 2 for us was actually getting to that break even. We got exactly to sort of that, we're just getting it, not making it worse. It just gets slightly better, right? And so that was sort of the point. And I'll say a little bit more about that in a second. So where is Google now? So that's sort of where we are on the Milestone. Recently, we announced our new generation of chip. This is called the Willow. This is a picture of Willow in front of Santa Barbara. I'm here in Seattle. There's nothing better than working for a team that is mostly based down in Santa Barbara. It's nice to go down there in the winter, like right now. And Willow is our new chip that we have developed over the last few years that is taking us, towards this next scale of scaling up to M3. And we'll tell you about the exciting performance and why we're excited about this platform going forward. So what is Willow? Well, it's a bigger chip, as Charina mentioned. It is important to get bigger, right? Like more qubits is better, but it's also a higher performing chip. So this is a chip that has 105 qubits on it. It's on this square grid, so each of the qubits kind of sits at one of these X's on this picture here, and it can talk to its nearest neighbor. So in the middle, it talks to the 4 surrounding neighbors. Some of them talk to 2 neighbors. And then one of the, you can see there's one off to the right here, which is only talking a very, very lonely qubit over there. But these are arrayed on this square grid. And this chip has achieved a pretty drastic improvement in what we call our T1. That's how long the qubits live before the quantum information decays away. So we can sort of ask, how long can we keep the quantum computing information quantum coherent? And in our previous chips, that was 20 microseconds, and now this has gone up by a factor of 5. This thing's uniquely designed for error correction, and I'll tell you a little bit more about that in a second. So what does this chip offer? Well, we can talk about what does it offer for the previous things we've done. So this is a plot of our Sycamore processor. This is the blue few chips here where we achieved milestone 1 and milestone 2. So Sycamore has been our workhorse, amazing chip, it's done a great thing. But by developing Willow, we've gone to this next step, and we've really seen this increase in this ability to preserve the quantum information. So this is just a picture of that on time for our processors. Is a big step, and we all like to see big steps in our performance, right? These are the nitty-gritty details. I don't think we need to dwell too much on them. One of the things about quantum computation that you should keep in your mind is you'll hear lots of different numbers. People talk about number qubits. They'll talk about the how long the information lives. What's the fidelity of the gate? Can you do it 99% of the time? Are you correct? Or 99.9% of the correct, right? So you'll hear all these things, specs. Now the important thing from an outside observer is to those specs are awesome. Everybody's making improvements. The real challenge for quantum computing and the way Google has approached it that's very different is it's really about getting all of the computation to occur at the same time. And we have a system that we've built that is very good at bringing up calibrating these qubits and running these big experiments where you're really trying to do, it's a very massive parallel system that you're doing. You're doing gates on most of the qubits at every cycle of your computation. And you sort of need to do that because the computation is falling apart on you. So you can kind of imagine doing lots of quantum gates between the different qubits is a good way to keep the information going. And so we've been able to achieve these great benchmarks in sort of this context of doing everything at once. So then you could ask, okay, how does this Willow compare on some of the previous tasks that we mentioned, milestone 1? So we reran the milestone 1 benchmark, which was this random circuit sampling, and we redid the estimates. As I said, people had made some progress on classical simulations. We sort of spurred an amazing amount of work in tensor network simulations to simulate these systems, and we redid that with our red team, which I think is a particularly good red team. They're very very good, and external collaborators help us on this, trying to attack this problem of simulating that quantum circuit. When we ran this thing again, we end up with an estimate which is that we run on our computer. It takes 5 minutes to run it on the quantum computer, but it takes something like 10 to the 23, 24, 25, some huge, it's 10 septillion years. It's a number so big that I stopped counting zeros at some point because it's just big. So we think that to simulate that classically with our best algorithms just is basically infeasible. So while classical things have improved, we all know technology always seems to follow this progression. We have sort of kept out in front of that, and just by this 5x improvements coherence time, we get this giant leap in the ability of how hard it is to simulate that. So the next thing we can talk about is error correction, and we would like to run now using Willow run error correction. So again, this is a sort of picture of what we're trying to achieve in error correction. So on the left, we have sort of the physical qubits and the fidelity, the number, the rate at which we have errors in our system. So right now it's like 1 in 1,000 or 1 in 100 times we get an error when we're running some certain little tiny gate, some single operation on our quantum computer. So what quantum error correction does is it allows you to take a bunch of those qubits that are not working perfectly and put them together and build this physical qubit. We use something called a surface code. So this is a picture of the surface code on the right. The circles are the qubits. There's data qubits, which is where we're going to encode our information, or we're going to encode one qubit into these data qubits. And then we have other qubits that we use to measure. And this is essentially going on as something like a refrigerator, where we're going to be measuring information to, measuring the measure qubits to do this error correcting routine. And that sort of keeps the system from the errors from spreading, sort of keeps it cold in some fundamental way. So the important thing about error correction is, as I said before, there's this thing called a threshold. What does that mean? It means if you have your error rate, if your error rate's really bad, error correction can't help you. If your qubits are really bad, you try to put everything together and it gets worse. So in this picture here, we have the physical error rate, and to the right is bad, and to the left is good. And then we can say, okay, we're going to encode quantum information into this system. And one of the things we're doing is we're encoding to something which has a different distance. So what is the distance? Distance is basically the size of that square grid. So distance 3, we have sort of a 3 by 3 set of data qubits in our system. Distance 5, we have sort of like a 5 by 5. Distance 7, we have a 7 by 7. So it's getting bigger and bigger. And what you see is, it's hard, blue, orange, green, right? What you see is, as things get bigger, as we add more qubits, when you have low enough error rates, your logical error rate, the thing that you care about, like I'm really protecting this qubit and making it really good, that goes down. So you actually exponentially suppress the error as you're scaling up in size. So that's the beauty of quantum error correction. It allows you to take a bunch of noisy qubits. If they're below this threshold, so if they're good enough, basically, then as you get the system bigger and bigger, your noise rate drops lower and lower and lower until eventually you can run computations long enough before you'll see no error in your quantum computation. This factor that it scales up by, this amplification factor, is called lambda. And you can think about Milestone 2 as achieving essentially lambda a little bit over 1, right? It's a little bit, or depending on how we define lambda, we have to be careful about the notation of how we do it, but it's basically at 1. We're breaking even, so we're right at that little black dot, or a little bit to the left of it. So in Willow, we could run the similar process of doing this error correction on this surface code, and when we did this, because the Willow has better performance, has longer coherence times, has better gates, there's a bunch of stuff, it's like everything in technology, there's a bunch of actual stuff going on behind the scenes to get this to work. When we run this, we actually see that we get a lambda, so the scaling factor that's not 1. Each time we go from distance 3 to 5 and 5 to 7, it doesn't sort of get just a little bit better. It gets factored by a power of 2. So from going to 3 to 5, it goes up by a factor of 2, and from 5 to 7, it goes up by another factor of 2. So total factor of a little bit over 4. So you can see this over here, and you can see the black line over here on the left. That's what we had previously. Like we have both the sort of error corrected experiment along with just sort of the bare normal experiment. They're right on top of each other. That doesn't get worse, which is great, but it doesn't get better. Whereas in the data in the red, and I guess that's bluish color, 2 blues, I guess that's a cyan maybe, I guess. The red is sort of the small code, right? We're doing distance 3. And then we increase the size of the code, and we see the error rate as a function of time, it gets lower. So this is a function of the logical error probability as a function of time. And then the final line on the bottom, right, is when we go to distance 7, it's decreased even more. And so what this shows is each time we're making the system bigger, our error rate is going down, which is awesome. We're in this sweet spot of going beyond this threshold of breaking even. It's even true that if you look at our physical qubits, if you just leave them and say, hey, I have a single qubit and I can use it and it has this error rate, that's this green line, the distance 7 numbers are actually below that. So we've taken this system that has an error rate, let's say it's 1 in 100. It's not quite correct, but let's say it's 1 in 100. And we made it 1 in 1,000 or something, right? We've made it better. So the promise of error correction is actually working. And this is sort of the first demonstration that anybody's ever done of getting below the threshold. So this is a picture of sort of that story. M2 was just getting break hold. The Willow chip has enabled us to sort of change that from, as we make it bigger and bigger, it's now got a slope that's going down. This is a log plot here on the left, right? So this straight line is actually an exponential scaling. So we've doubled each time. Where do we want to go? Well, the next step is Milestone 3, which Karina showed on her slide. Milestone 3 is trying to get to a qubit that has 1 in a million error rate, right? Which is, so you can run something for, 1 million gates before you see an error. And in order to do that, we'll need to increase our lambda. So that means make even better qubits, keep working on this. We have the qubits, they have better coherence time. We can keep working on that. There's a lot of technical things you can do to keep pushing on that direction. But then the other thing is start scaling it up. So instead of doing 100 qubits, right, you'll have to start scaling up more and more till we get to around distance 15, we think. We start to cross into this thing, we'll hit milestone 3, and we'll have distilled now a really, really, really good qubit that can be, sort of useful in the long run for quantum applications. Okay, so that's sort of where the next step on our path. What else are we doing in this space? We have this nice Willow processor. We have the Sycamore processor that does all the things. What have we been doing that's sort of like useful beyond just sort of doing these things of this long-term story of building a quantum computer? Quantum computers are right now really useful for people who are physicists who want to like do simulations of systems. This is a plot of a bunch of publications that our team has done. Essentially, we have a fantastic team of physicists who want to understand things like materials or molecules, or even things like learning from quantum data that Charina mentioned. And they want to actually take the current systems, the noisy ones, and see how far they can push this. And why you would do this is we're at the point where our chips are good enough. They're starting to get to the regime where, again, we knew from the circuit sampling that it's hard to simulate them. And we can start to do things which are hard to simulate or very challenging to simulate, that start to answer hard scientific questions. Sorry, I went forward one more. So we're asking questions about these physical systems. These are the type of things that we will be solving. I put my head forward in time to when we have a large error-corrected quantum computer. We'll be using this thing for simulation. These are sort of what people will call NISQ applications. And the real sweet spot here is for applications for things that physicists in particular and chemists care about, is these simulation type ideas, and trying to push ourselves into that regime. So to this end, who do we work with today? Who's our most important, what is the product that we're doing? What we're mostly doing is working very closely with, internally on these projects, but also with external users. So we have external users who run on our quantum processor. They access the machine. Like many of the other competitors out there, you come in through, basically through the cloud. And these customers work with us, and we work together to try to see if we can solve their hard scientific problems more efficiently than they could if they were using classical computers. So these are some of the cutting edge people pushing the limits of sort of what quantum computation we do, sort of what big volume can we do, but also trying to have a practical bent of like, what problem are they trying to solve? And so we take these users in and work with them closely to try to see if we can push into this regime. Because again, this is a part where when we're into a point where we're starting to get into discoveries, right? And discoveries are weird because discovery is a pathless land, right? You have to walk somewhere that nobody's walked before. How do you do that? Well, you have to kind of do it. So our approach here is to try to identify people who are really walking on the boundary and have a diversity of different opinions about what we should be doing to try to push ourselves forward, and they can help us get there. And that's where we sort of work with these external partners. We do have a bunch of experience working with. If you are someone who's listening who works in that sort of area, wants to get in contact with us, please use this email address here, and we will get back to you. We're always looking for people. We really like to increase the diversity of people who are doing interesting things, because this is sort of trying to push us into the next stage of useful quantum processors. And with that, I'll hand it over back to Charina.
So how to think about everything that we've talked about the last 40 minutes, and consider what have we done, where are we going? One picture is a graph like this. You could see on the x-axis is usefulness, how useful is the actual problem being run, and then on the y-axis, difficulty. And you can see gradations along that y-axis, right? Beyond brute force, taking days on a workstation, all the way up through classically expensive and classically intractable. So to put this all in context, right, the random circuit sampling problem that Dave talked about, this is one that has been demonstrated to be classically intractable. However, it's a benchmark problem, right? It to date doesn't necessarily have clear commercial or other application. It really is something we're using to benchmark. So it's far to the left on the x-axis, but above classically intractable on the y-axis. A number of the other experiments that Dave showed, right, and a lot of things that people are running now, which are really interesting scientific discoveries. A lot of cool things happening on today's current processors. However, it is important to note that nothing to date that has been experimentally reported has been beyond classically expensive, right? So this is yet, quantum computers are an interesting new tool, not yet beyond what's possible, with months on a supercomputer. Demonstrating quantum benefit. So, we highlight this here in the upper right-hand quadrant, something that is extremely difficult, beyond classically expensive, and also, commercially relevant, has real-world usefulness. This has yet to be seen, right? And of course, this is something that people are all very excited about. It's a reason that we're really pursuing quantum computers, because we believe that they will help to deliver items here in this upper right-hand quadrant. But that is still something we're working towards as we continue to push the performance of our system, and of course, also as we continue to develop better algorithms, more efficient algorithms. So even as we work to do that, we are working with a number of partners to develop applications for fault-tolerant quantum computers. Right, we're making progress along milestones, milestone 3, 4, 5, and ultimately milestone 6. And even as we do that, in the meantime, we're working very closely to make sure that we're developing the right algorithms, the right ways to use the computer once it's ready. And you can see a number of applications here very much related to how we opened this conversation, looking at things like quantum computers for drug discovery, battery design, catalysis, fusion reactor design, and more. So a lot of different opportunities there. How else will a quantum computer be used? Of course, right? If you think back 40 years ago, 50 years ago, nobody would have ever imagined all the different ways that we, as a society, are using classical computers today. We expect that very much to be the case for quantum computers as well. And Google has partnered with X Prize to launch a prize in quantum applications, looking at all the different ways that new algorithms and applications might be developed using quantum computers. We're excited about that, and we're very, very much excited about continuing to partner with and grow the developer community to pursue new applications. Finally, what's left, right? We hear about, what are the remaining challenges? You can see a number of them here. Happy to go into more of them in detail in the Q&A. Improving qubit quality, right? How do we continue to make every single one of our physical qubits better? How do we look at scaling to larger chips? Not only do we have to make the chips larger, we have to make all of the supporting infrastructure, right? The dilution refrigerators, the wiring, all of those things have to scale. How do we think about supply chain development, right? A lot of these computers, there's multiple components, very complex. No one company, no one country can be the expert of all of that. So how do we continue to work with and partner with experts across the supply chain? Workforce development, a lot of this requires, specialized skills, and we've been working with a number of universities around the world to really make sure that we're building up talent in the right way. And then finally, and of course, very important for this call and the community on this call is applications development. Really thinking about all the different ways quantum computer will be useful is going to be critical to have that developer community. We'll end with this quote, also from Richard Feynman, and then we're very happy to have a Q&A time. Richard Feynman, talking about the development of a quantum computer, says, "By golly, it's a wonderful problem because it doesn't look so easy. It's extremely difficult. It's really, really hard problem, but we love working on it. It feels very ambitious and very exciting, and we feel honored to be part of the journey." Thanks.
Great. Charina, Dave, thank you so much for that presentation. That was awesome. Lots to digest there. I want to encourage our attendees to submit questions in the Q&A channel now, but I'm going to kick off with the first question here. So Dave and Charina, you did a wonderful job of showing how it's already being used in science. I think Dave's slide had a dozen papers in science, nature, nature physics, etc. And then Charina, you had a chart with 3 quadrants of applications, but that elusive 4th quadrant. So I'm going to ask you the obvious question. Which of those applications, I believe it would have been on the right side of Charina's chart, do you think might be first to scale up into that 4th quadrant? Do you have any kind of gut feeling right now? And I don't want to ask you any NDA information, but just anything you have a hunch as to where you think we might see that first real useful quantum success that also exceeds classical computing capabilities?
Yeah, I'll jump in. Thanks for the question. We are very much excited about this. I think the entire field of quantum computing is very eager to see something
Sure.
in that upper right-hand quadrant. Our best kind of estimate right now, and there's been a lot of work on this, is that it's likely to be in a chemistry or physics-related problem. And so we're working with a number of collaborators on this. We expect to have more to say as early as later this year.
Okay. Got a question coming in. This is a straightforward one. Jorge asks, why the name Willow for your new chip?
So I mean, the great thing about new spaces, you get to define your own naming scheme. So sycamore is a tree, right? So all of our choices have been named after trees in California and Santa Barbara area. You'll also see that we have these beautiful dilution refrigerators, which are painted with UNESCO World Heritage sites on them. If there's something actually wonderful about this, we don't have the big black monolith of a supercomputer, right? The quantum computers, because they're simulating nature, it kind of makes sense that we're doing the motif of natural things, and so it kind of feels good. And it's gorgeous to go visit this place. If you just look at this picture, it's amazing to be able to work in this space.
Great. And Jorge has another question. Can you briefly explain why quantum computers are a concern for classical encryption? I suspect a lot of our attendees know that, but I'm sure many don't. So can you give the simple explanation of why quantum computers threaten classical encryption techniques?
So I can take that one. So the major discovery that set off quantum computers, so there were early ideas about maybe we could build this thing, but in 1994, Peter Shor showed that quantum computers can efficiently factor numbers. So you have a large number, you need to break it down into, say it's the product of two prime numbers, you need to figure out what those prime numbers are. Classically, we don't know an efficient algorithm to do that. This problem, the hardness of this problem, is the basis of public key cryptography. So whenever you go to your browser and you see a little secure link and you're communicating over the, using the secure internet connection, what's being used there is one of these algorithms like this. And quantum computers can break a bunch of these public key crypto systems. Now that's the scariest news, right? Like that's one of the reasons why a lot of quantum was funded in the early days. This is a national security issue, right? It breaks this cryptography. In the meantime, people have developed what they call post-quantum crypto algorithms. So these are algorithms whose hardness are problems that quantum computing people haven't been able to break them. So people like me, used to work on this, is one of the things I worked on. Like, a bunch of my friends who are way smarter than me. You shouldn't trust it just because I worked on it, but a bunch of people who I consider, very, very brilliant mathematicians, they know all the stuff in these books, right? Like have tried to break that problem with a quantum algorithm and not succeeded. And these are post-quantum crypto systems. And there's a big effort now because quantum computers are, we're on the path towards building them. So we need to upgrade our infrastructure for all these post-quantum crypto algorithms. That's a big space that's being developed across the industry.
Yeah, maybe one other quick thing I'll plug. I think people may be aware, but the US NIST agency, the National Institute of Standards and Technology, has really recognized this as a problem over the past decade. They have been leading the charge on developing, sourcing, and really publishing these algorithms. So they published the first set of 3 post-quantum cryptography algorithms last summer. Encourage everybody to take a look, and they are encouraging people to already start implementing these. And of course, the search and the development will continue over the next many years.
Great. You've mentioned Shor's algorithm, and of course, it came up in the context of that last question. I noticed you didn't mention Grover's algorithm, which is useful for search, and you all are Google. So do you want to comment at all on any efforts Google is undertaking to improve search with quantum? Or can you talk about that?
So I could say a little bit. So Grover's algorithm is an algorithm for querying a function and finding a marked element in that function, and it does it quadratically better, meaning it's, instead of n, it's like square root of n. So it's a great foundational algorithm. It has a lot of applications. There are a class of algorithms that people will call, you hear quantum amplitude amplification, which is sort of the generalization of this thing. There's a bunch of places where people have identified algorithms pretty much ubiquitously across different fields, but they give this sort of not what we call exponential speed up. So it's not like 2 to the n versus n, right? It's n versus square root of n. Our team focuses a lot on this quantum computer that we're building. we're still competing against classical computers. So a quadratic speedup is good, but it's not great. When we do the analysis for most people's platforms, including ours, you really need to get algorithm improvements which are like into the fourth versus in, or in maybe into the third. So our focus, and where we think there's actually a lot of impact broadly across computing, because these algorithms, you know, you said search, but it's everything that Google does, right? Is touched by algorithms that are sort of this combinatorial nature. Where we're looking for problems are ones where we have this super quadratic greater than this quadratic speedup, and we believe that's the place to focus. These things really, because you're computing against classical computers, they really are farther over on the timeline, because you need a really, really good quantum computer to do that, because classical computers, you know, are awesome. They're great. They're, you know, allowing this conference call, and we're competing against a, you know, an industry that's going for 50 years. So that is on the timeline, but it's further, I would say, very much thought of as further over the right, and really trying to find these super quadratic speedups.
Dave, I'm glad you brought up that point. I think Scott Aronson, when he gives talks about mathematical algorithms and achieving useful quantum, he talks about that as well, talking about the need to find algorithms that are useful, but that scale as high order polynomials or exponential, not as lower order polynomials. So thanks for sharing that with our audience.
I'll say one more thing there, because it's a good thing. Scott's an old friend of mine. The other big interesting area is what we would call early fault tolerance, right? So we have this error correction experiment. We're building up to get this 10 to the 6 qubit, this very long-lived qubit. Now you can start imagining, okay, maybe we have 100 qubits. So algorithms for very small but error-corrected computers, so they go for a longer depth, right? That's going to be an interesting space, because that's, you know, that's different than sort of this long-term, like really getting the scaling to work. But what are going to be the first fault-tolerant algorithms? There are a lot of smart people working on this right now. It's a very vibrant part of the field. And we think that increasing focus on these sort of small first fault-tolerant algorithms is going to start taking over as being, because we're going to be able to run them. What can we do? So we're excited about that era as well.
All right. And the last question before we move on to closing comments is about these techniques that you've demonstrated here that help you manage noise better, especially with higher fidelity qubits and a larger number of them, being able to deal with the noise and errors better. How much of this is specific to Google's approach, and how much of this will benefit the rest of the quantum computing vendor community, not just the other supercomputing qubit vendors, but other modalities as well?
Everybody has to do error correction, we think. There is no magical qubit. No one has found one. Each company has a different approach. As was mentioned, ion traps are a big platform. There's photonics. So PsiQuantum's a company that does this. Microsoft, for instance, is pursuing Majorana qubits. Every quantum computing platform has its own, everybody has a word you can say that makes them nervous, or a few words, and everyone has a different performance and trade-off. We strongly believe superconducting qubits are like a really good, you know, if you're going to place bets, you want to place on them. But they all, in order to really scale, you know, we can probably, you know, this question about finding useful applications is we can get to this era where we can find interesting things, but technology is all about scaling and getting bigger and bigger problems that you can solve, and sort of constantly pushing this. And to do that, you really do need error correction. And the different ways you do the error correction might be different. Like we're doing a surface code, which is very nice for 2D surface. You might think it's good for 2D geometries. Our qubits sit beside each other. But different platforms might have different error correcting trade-offs, and they will have different technology trade-offs they're playing to get that to work. So it's exciting, just to say this, it's probably the most exciting. I worked in error correction. That was my PhD thesis, was in quantum error correction. I've been in this field for a long time. I left and came back, but like we are entering the new era of error correcting experiments. And it's extremely exciting as someone who used to talk about the theory 20, 30 years ago. Right now it's like, hey, we're actually doing experiments. So there's that's the stuff that I think if you're watching from afar, watch the error correcting experiments, because that's where the fun, exciting new stuff is occurring across all platforms. So
thank you guys so much for your presentation and for answering these questions. Really appreciated having you here. Hope we can have you back in the future. Hope to keep seeing big announcements made, like the big Willow announcements in 4Q. I think it got a lot of the community tremendously excited about the prospects for quantum computing achieving real world value in their careers, not after their careers. So I think it really got a lot of people interested in evaluating whether they have problems that are going to be useful in the not so distant future, that for which quantum systems will be useful in the not so distant future. So thank you very much for that.